All right, good morning, everybody. Today is the last day of September of 2024, and we are in ES 1060, Engineering, Computing, and Problem Solving, and we are going to start using my favorite program by default, Excel. And so far up to this point, we have been working with MATLAB, and I just went back through, and a couple of you have not turned in your final code. So please make sure that you turn in your final code. I also, with one student, he and I have conversed, it's nobody in the classroom right now. I had trouble reading his PDF. I couldn't do that, so I asked him to submit it as a .m file. And I haven't had a chance to review that yet, but I'll go through that as well. But please get your code into me as soon as possible. It was due Friday, so I'll check again probably Wednesday to see if it's in place. And if you need feedback on your draft, please let me know. All right, so MATLAB is basically the structured programming language that engineers almost stereotypically use. So, but it's extraordinarily versatile. It does not do everything the best, but it does some things extraordinarily well. And so now you've had a smattering of MATLAB, you've done the onboarding, you've written a couple of pieces of code, and you understand how to write custom code to solve a problem that you have in mathematics, and how to input and output, and how to do decision structure. And input, output, and decision structures are pretty universal to all programming languages. So what you've learned with MATLAB will benefit you whether you work with Python or any other programming language. They all have some similarities. They all have some things that they're better at than others. But basically, we're going to put a period on MATLAB and start over with Excel, or not start over with Excel. But why Excel? Well, the first thing is, the first thing about Excel that's extraordinarily important is it is nearly ubiquitous. Oops, ubiquitous. Who knows what ubiquitous means? Ha! And if I spelled it, I think I've spelled it correctly. Ubiquitous means it is everywhere. Okay, so ubiquitous is just a word meaning regardless of what engineering firm you work for, regardless of what college you go to, regardless of what platform you have, you are almost assuredly going to have access to Excel, because Excel is part of the Microsoft Office suite, along with Outlook, Word, PowerPoint, etc. So I think it's really important to use it, because you may go to work for a firm that has some dedicated software. So for example, if you go to work for the highway department, they have a lot of programs that will help you design highways, calculate, cut and fill, and so forth. But everything that you can do with almost every other program, you can do with Excel if you are determined enough. As Dr. Tim Glatzer says, Excel is not the first best tool for anything, but is the second best tool for almost everything. And so for that reason, and the fact that it is ubiquitous, it's very important for you to be able to put it through the paces. The other thing is about Excel, and one thing that I love, the genesis of Excel is, it used to be the first spreadsheet program that came out back in the 1980s was called Lotus 1-2-3. And then it evolved into part of the Microsoft suite called Symphony. And then it dumped out as not quite a standalone, but a very impressive program called Excel. So it's been around since the 1980s, maybe the 1990s. So it's been around for approximately 35 to 40 years. So let's just say 40-ish years. And it has done nothing but improve as time has gone on. So Excel existed before the graphical user interface was common. Apple was using a GUI, but Microsoft and dot was still DOS based, and everything was line by line coding. And back in those days, if you're ever interested in a history lesson, take a look at your keyboard, and the keys up here, the F keys. There was a template that you would put here, and it would tell you, like, if you push F1, this is the function that's going to happen. And they also had Shift F1, Control F1, and Alt F1. So there was a stack of 4 functions that went underneath each one of the F keys, and they were commonly called the effing keys, because it was quite a cumbersome thing to keep this template in place and to remember all of this stuff. Now it all happens within the interface itself. So the first thing is, if you open up Excel, let's see if I want to do any of these. Oh, those are all things. Okay, so if you go to the start button, let's go ahead and share and see how much of my sharing we'll do here. All right. So if you go to the start button down in, generally speaking, the lower left, you'll have all of the apps in alphabetical order, and under E will be Excel. So if you open up Excel, what it looks like is just a bunch of rows and columns. We'll talk about this in just a moment. But anyway, the thing that I want to bring up is, right now, some of you, if you've used Excel before, like if you've done sums or columns or little just small projects, some of you may have done more, but if you've done small projects with Excel, you may have one idea of what Excel works like, and it's awesome for those things. I store everything. I store budgets, and I store projections of money, and I do amortization tables and so forth in Excel, like if I'm selling or buying something with a note, and I keep it there. And actually, that was a project I did way back in, 1990s. I wrote an amortization schedule for some realtors, and actually made quite a bit of money doing that, and I did it all I did it with Symphony 1 through 3, actually. It wasn't even Excel at the time. But there's a lot of features that are very simple, and then you can really boost it up. So there's 3 basic ways that Excel works. It works like a spreadsheet. Well, I guess 4 really. It has what's called data packs, so that, like, if you have statistical things, you can analyze statistically in Excel to a very high level. You can also use macros, which are automated functions. Like if you want to do the same thing over and over again, you don't want to keep telling it, multiply this by 5, multiply this by 7. If this number is 6, if this was 6 and smaller, multiply by 5. If it's 7 or greater, multiply by some other number, whatever. You can automate that. So you can just run a macro. And then the last thing that Excel has built into it is an actual programming language, which is called Visual Basic for Applications, or VBA. So you can take it to an extreme. So if you've worked with Excel in the past, the first week or 2 that we work with Excel may seem quite simple to you, which is great, because lucky for you, but it's not, it won't stay that way. So please take my word, I will teach you some new things. So instead of the effing keys, what we have here is we have a drop-down menu, and we also have a ribbon. All right. So each one of these things, we won't become familiar with everything, but all of these are different ways of doing things in Excel. For example, this symbol sigma is a summation key, and you can see that under the drop-down menu on this tab, we have some average, count, max, min, and some more functions. So if you look at these are all statistical functions. So like you could put together a table. Let's just do this. I'm going to do this really simply, but like, let's just start with 1. And then I'm going to, here's an automated function. I could go 1, and then if I wanted to just do a numeric list, I could go 2, 3, 4. But if I don't want to keep typing that in, I could put in the next cell. Let's just take a look at the cell above it, which has a number A4. That's the cell address. And I want to add 1 to it. Okay, so I get 5. So then instead of typing 6, 7, 8, 9, 10, 11, 12, I can just fill in the blanks with that and just have a list of numbers. All right, now, if I wanted to, I can see by this, obviously, that my greatest number is 25. But if I wanted to see what the greatest number was, if it was mixed up, or if there were a whole bunch of numbers, for example, I can sum them up, okay? And it's guessing that I want to go from the top to the bottom. I could also pull down and ask it for the max. She says she could. There it is. Now I have to, when it has parentheses like this, you have to put in where you start. And I believe I started up at cell A1 and I ended at cell A25. Let's see if I got my syntax right. No, it doesn't like that. A1. So I have to go take a look here. It says number 1, number 2, number 1, number 2. There's a period there. That should be max. A1 to A25, comma. There we go. And it comes up with the maximum. I could also do the minimum, right? Which is going to be 1. And then I'll show you what, and I could do minimum works the same way. Now it's going to guess, but it's going to go for A20 down to A27, which is that last number that I calculated. So I really just want to go up to A25 because that's my data. There you go. And it gives me a minimum. And I could also do a statistical number, which is just the average. So the average is just going to be adding up all of those pieces of data. Now I'm going to go all the way to the bottom and dividing them by the number of data points. So obviously that's a lot easier than doing that by hand. You can do that all by hand, but it's all there. Now within that tab, within that summation tab is where it says more functions. Those are going to be statistical functions, right? So you can see, you can count the numbers, you can do like, let's take a look. If you don't know what something is, like SIN of a number returns the sign of an angle. That's pretty cool, right? So you can do all of these things. You can do payment calculations where you put in a rate, a net present value, a future value, or whatever, and you can get out how much payment would be on some sort of thing, which is what an amortization schedule is. If you buy a house, $285,000, the interest rate is 6%. How much you're gonna have to pay a month to pay that off in 30 years, in 40 years, which is a horrifying thing because you think you're gonna be in your late 50s by the time you get that thing done. But so you can pay extra. You can also like put in, if you pay 50 extra bucks a month, it's gonna take a whole bunch of time off of that loan and so forth. So it's kind of fun to work with things like that. Anyway, so Excel in its rawest form looks like this. So the next question is, and this is where we're gonna get back into to engineering problem solving. But let's see if I can get this thing straightened out a little bit. Yeah, that looks pretty good. All right. So the question is, why use Excel? Well, there's a couple of different reasons to do that. One is speed, and the other is optimization. In other words, if you have the ability if you don't have the ability to iterate, meaning try something else, adjust a value, put it back in. If you're doing all that by hand, you're probably going to tap out on how much time you have to devote to that more quickly. So if you have something that will automate part of the task and you have a chance to try different values, you're going to come to a more optimal solution based on the fact that you can do it more quickly and with less drudgery. So this also comes back to the difference. Like I was telling when Mrs. Spinney was in here, we were talking about, and I said, math is the biggest tool that engineers use, but it's not the only tool, right? The difference between engineering and almost anything else using math, well, let's just see, engineering and a theoretical or pure science, let's just say a theoretical science. Because engineering is an applied science. We use everything that's available. We are not constrained to using a particular area of study. And the other thing about engineering is we are always describing a real world or nearly real world situation. Okay, which is why I get so adamant about an answer is almost always a number plus a unit. 72 is almost never an answer. $72, 72 kilowatt hours, 72 miles per hour. Those are all answers and they all mean different things. So math is our first biggest tool, but it's not enough. It's just not enough. We have to take into account all of these other things. And that's where Excel can help you, right? So Excel is awesome at doing remedial math. All the stuff that you learned when you were in middle school and maybe when you were a freshman in high school, Excel will do it for you. But Excel never misses. If you tell it what to do properly, it will never make a mistake. Okay, so any mistake that you make in terms of math will be your mistake. So that is a comforting kind of a thing. So when we talk about Excel as an engineering tool, which is what the rest of this class is all going to be about. What that means is we want to use Excel to solve problems. Okay, and that means that we need to take something else into account. The answer to a mathematical question is not always equal to the solution to a problem. And fundamentally, this is where engineering rubber hits the road. Okay, so what that means is you learned this when we did the temperature conversion scale. You can get an answer to a mathematical problem. For example, degrees Kelvin is equal to degrees Celsius minus 273, right? This is whatever you put into this and you get out is the answer to a mathematical problem. But if degrees K is less than 0, it is not a solution to a problem. Because although it makes mathematical sense, it does not make sense in the real world. You have a physical reality barrier. That temperature cannot be below degrees 0. And there you go. So this has been described to me, and I can't say I really fully understand this, but I'll present it to you. There are certain things that seem like they should be artificial barriers, and certain things that really are artificial barriers. For example, when they used to talk about the sound barrier, there was a speculation about whether an airplane or anything else could go faster than the speed of sound. Well, it can, absolutely. But what happens when you cross the sound barrier, or Mach 1, which the speed of sound changes a little bit based on the density of the air, caused by some things, altitude, temperature, blah, blah, blah. But basically, when an object flies exactly at the speed of sound, there's a shock waves that's set up that's very difficult on the equipment. But once you pass through the sound barrier, it's Mach 1, everything kind of goes, it doesn't reset. Some of the parameters change, but everything smooths out. So the deal with going through the sound barrier is getting past it. There are other barriers that we cannot seem to get past, such as the speed of light, right? And absolute 0. Now, the speed of light is the subject of much talk in scientific and science fiction communities, because if we can't travel faster than the speed of light, we probably will never be able to reach another planet. So that presents something that to a person with an exploring nature sets up sort of a conflict in their mind. Now, there are things that you could do. For example, if you travel close to the speed of sound, space itself, or if you travel close to the speed of light, pardon me, time itself actually contracts. So if you were able to travel fast enough, even if you can't travel, your object doesn't tell you that you're going beyond the speed of light, you're actually covering more distance because time has changed. And this can kind of be exhibited in what's called the twin paradox, which is a thought experiment. But basically, if you have an identical twin and one of you is an astronaut and one of you is in mission control, the identical twin that travels into space, if he or she travels at or near the speed of sound and comes back, he will actually be younger than his own twin. Okay, and that's, well, it sounds flaky. It's mathematically and scientifically a proven kind of a thing. There's some technologies, the only technology that I know of really that compensates for traveling near this, for the dilation of time, are satellites. GPS has to compensate for the speed of light, approaching the speed of light, time dilation effect. But so these appear to be true barriers, okay? And perhaps looks mathematically like 0 degrees Kelvin is another barrier that we just can't cross. Well, the way it was described to me by somebody with a different kind of a brain than me, because I don't understand this, but it's kind of like if you're traveling on Earth and you think about the compass rose and you travel north. Well, north is an absolute. In other words, if you use this cardinal direction thing and you travel a little bit this way, you're traveling less north. And if you're traveling a little bit this way, you're traveling less north. So north is as north as you can get. That's how this was described to me. The speed of light is the speed of light. And you can't, if you veer off of it, you're going something different than the speed of light. So I don't really know what that means, but it's an interesting correlation. All right. So when we get back to our ideas with Excel, we are going to focus on, in chapter 1, we're just focusing on Excel basics. And there are 11 problems, 1.1 through 1.11, which we're going to be covering this week. And then next week, probably since my pattern, we're going to do chapter 2. When we get into some of the more difficult chapters, we may not do a chapter a week. But for now, we're going to do a chapter a week. So today, we're going to talk about just sort of this philosophy of what Excel can do for us. And then in lab, we're going to start working on 1 through 11. And if you are familiar with Excel, you're probably going to be able to get this done today, which would be really cool. Or I shouldn't say probably, you may be able to get it done today. If not, you may have to work on it till the end of the week. And then this will be due by Friday. All right. So then, but basically what we're talking about is 2 different things. We're talking about problem solving, and we're talking about execution in Excel. So the first thing is, all of you people in class at this point will have to purchase this textbook. And I think you can do it online, or you can do it as a hard copy or whatever you like to do. But I have the PDFs up here. I can't keep them up. Oh, I rotated you. You didn't do what I asked you to. All right, there we go. Anyway, so chapter 1 just steps through this whole idea of thinking about problem solving techniques and so forth. But what you'll see is, this just talks about, do you remember how I said when you do a problem, you need to do a free body diagram, you need to state your assumptions, you need to do all this stuff. Well, when you're doing a math problem, you probably start at about step 5. In engineering, you have to set up the whole problem. You have to set up what you're dealing with first. And so the first part of this chapter right here just talks about how it's an approach to engineering problem solving. And I always think this is very interesting because this is something that sometimes people resist because it takes you a long time. If you're going to do a problem right, you really do need to spend a little bit of time contemplating what you're trying to solve, because it's not, as I said, the answer to a mathematical statement. It's a solution to a problem. It also strikes me, something else that was said by a different person Lucas Shaw, who works here in our computer sciences, our computer services department. Lucas Shaw said there's two ways to approach problems, and one is a project management way, and one is what he referred to as the cowboy way. And I thought this was really interesting. I had never really thought about this before, but what we're really doing here is coming up with a manner to do a project management way. And what Lucas meant when he talked about this was, you can either have a systematic approach to solving a problem, you know, so that your company always does things the same way, or if you are, especially if you're working for yourself, the cowboy way is super because you can just bypass a lot of stuff. But when you are working with other people, you need to make your work reproducible, and you need to have a way that your company does things that looks the same so that your clients know what to depend upon. Okay, so even if you're doing research or something really raw, you still need to have a way that you can approach it, because quite honestly, you need to document your work, and you need to make it so that the next generation people can follow you. Or if you make a mistake at step 11, then maybe somebody can come in and say, yeah, steps 1 through 10 are great, but here at 11, I would try something else. And they can take your work, and instead of starting the whole thing over again, they can start maybe at step 11 and come up with a different path that may be a solution to the problem as well. But so what we're trying to avoid here is the cowboy way. Now, if you are I was thinking this morning about my husband, who's an engineer, but he runs his family farm, getting ready for beets. When David is getting ready and he works on equipment, he can kind of do the cowboy way because he's working by himself. When harvest comes up, it's all project management, because you got to have 6 truck drivers and somebody driving the topper, and some of them are going to school, and so they can't be here Tuesday afternoon. Some of them are retired guys, and they have, you know, board meeting for the hospital on Wednesdays or whatever. So you have to manage everything. So you really have to switch back and forth. But this can make you unhappy or happy, depending on, I think it has directly to do with how many people are working with you, but that would be my opinion as well. So what we're talking about here is developing a technique for project management. So when you do stuff and you're working through things, read through these steps. And then at the end, the last step here says, make sure that your solution is clear and complete, presented in an orderly manner, results labeled, units included if it's numeric. Is logic used to obtain this? Is the logic clear? And if you can, tables and graphs are just awesome because there's so much data that you can put into those. But the other thing I would say is at the very end, look at your answer and see, does this make sense? Because that's really the answer. It's kind of like when you're building things. If you look at this building, for example, this building was completed in 1993. And it's fine, it's a good building. There's some problems with it, but we built the walls out of cinder blocks. Okay, I wasn't here, but I'm saying they built the walls out of cinder blocks. Cinder blocks is a building material that some people like to use a lot. There's some advantages to it. One of them is they're all the same size. So you don't ever have to cut, you just have to cut on the very ends. You don't really have a lot of, engineering to do as far as that goes. They're also very sturdy, but they're reproducible. There are other building materials that are awesome, but they may be more expensive. Like, for example, you look at an acoustical ceiling, cinder block walls. That's pretty utilitarian, right? If you look back in old buildings, like if you go downtown, even here in Powell, there's some buildings that have like tin tiles that are pounded and embossed for the ceilings, which are really cool. Not really a practical building material, but they were at the time. Or another thing that I really love is, and I'll just ask you what you think about this, but a lot of buildings back in the old days were built, generally speaking, on the upper part of the walls facing a street would have glass blocks. They would use glass blocks in construction. Glass blocks are really tough for construction, in my opinion, because they're not very stable. And when you use small ones like this, they kind of shift a little bit. I find them to be artistically really pleasing. But 100 years ago, what do you think would be a major advantage of having glass blocks in part of your wall? Yes. Oh my goodness, absolutely. Light was really expensive and hard to come by. So you wanted to get as much natural light. Natural light right now is not that big of a deal because we have electricity now for 80 plus, well, let's see. Yeah, rural electrification came through in the 1940s. So yeah, 80 plus years. And some people had it before then, but you know, it was really kind of hit and miss. But before cheap central lighting, people were lighting things with lanterns and candles, and how they didn't manage to all catch on fire is just absolutely beyond me. But yeah, so natural lighting was a big deal. The other thing is sometimes if you go to an older city, there's nothing like this in Powell. Can't really think of anything like this in Cody, but something will come to me when I see one. I'll let you know. Take some pictures for you. But you'll see sometimes you'll see glass blocks and sidewalks, and that generally had to do with there was some sort of business underneath on the lower floor, you know, and they would let light in that way through those light tunnels as well. Now, the other thing with that is why would they put businesses underground? Well, primarily because people did not have cars and walking was difficult. So people lived near their jobs and they lived near their shopping, and that's the way it was. So you tended to build up a couple stories. And if you have good bedrock, good foundation of some sort, building down and building up is a lot better for business than it is to just sprawl. You know, Powell there's sort of two different kinds of towns too, and then I'll stop about this. One of the most exciting things to me, I travel a lot. I get to go a lot of different places. I go to exotic places and to mundane places, but I always look at what's going on. Okay. Like we were in Newcastle a couple of years ago, and I was looking around. There's a really old business district in Newcastle that's very interesting, and maybe they even have some glass blocks there. But when you look at places, you can kind of see how they came about. And in modern times, there's sort of two different kinds of town. There's towns that are built around a central business district, which are called hub towns. And then there are towns that are built along railroad tracks, which are called railroad towns. Powell's definitely a railroad town. You know, things are stretched out. And, oh, here's another question. Let me ask you this. If you, let's say this is north, because it is behind me, okay? If you look at all the streets in Powell, they tend to run this way until you get to Coulter Avenue, which runs like this. Why does it run like that?
Where's Coulter Avenue?
It's if you drive straight south, they call it the 4 lanes, but like if you drive down Division, and then there's a big street, it's actually the highway that runs to Ralston and to Cody. If you go this way, you'll head up at Ralston. And if you head up this way, I'm drawing it in the wrong place, Ralston and what's over there, Garland. Okay. Anyone know why it does not run north and south? Anyone ever look what's over here on the side of it, on the south side, south-ish side? Say it. Yes, train tracks. And also, yep, the canal. So what happens, canals and trains kind of do the same thing, but water more so. Water's more insistent. Water always runs downhill unless you pump it. Don't ever doubt it. It will, and if you pump it, it's expensive and you will be maintaining it forever. What water does naturally is run downhill. And specifically, this canal is meant to feed irrigation districts. So they don't want it to just slurp from one end to the other. They want it to run at a certain rate. So they put it on grade, which is generally about 3% of drop. Okay. But so the water comes out of the Buffalo Bill Dam and it runs clear down. It runs into, I think it might even go to Lovell. I can't remember. Does it go, do you know? Do you guys get water in the municipal from Aquavia? I don't know, I'm asking you, I don't know. Okay, that's fine. I don't either, so, so we're on the same page. But there's a lot of communities that are fed water and a lot of the farm fields are fed water. So the water has to run on grade. So if you had the canal not on grade, the water wouldn't run. trains are a little bit more forgiving, but they do the same thing. And trains came across the United States at a time where they have what are called American Railroad Schedule. And I've read these things when how they surveyed and built in railroads. Oh my gosh, those people were so smart. I do not even know how they ever did that. But everything has to stay on grades because trains have to go, they can only go uphill and downhill at certain grades, and they can only go around corners at certain rotations. Now there's ways to get around that. For example, in the mining towns in Western Colorado, Silverton, Durango, they ran a narrow gauge railroad because they can turn corners more quickly than a standard gauge railroad. But I mean, railroads are like humongous engineering feats. Biggest grades are in the southern part of the state, and they have all those big boy engines. And that was the challenge, was to get from Sydney, Nebraska to Laramie, Wyoming. That was like the biggest engineering challenge that came about. Anyway, I got carried away again, but that's the way it works. Everywhere you go, pay attention to what's going on, and you'll just see the most amazing things. But anyway, so yeah, so when the canal came through, it has to be on grade. Train comes through, have to be on grade. It would be really ridiculous to make Coulter Avenue look like this, because then you would have to put a bridge over everything all the time, right? And so it makes more sense than to stick with the idea of a cardinal direction, to just put the road right next to the railroad tracks on the same grade. So there you go. And we do that a lot in engineering. We build on what happened before, and that's called infrastructure, and that's the way things work. So you'll see a lot of times where a telephone line and an electrical line will follow a railroad, which used to have telegraph lines, and then the roads follow, and that's just the way it is. So
you just want to also avoid train tracks, because on the highways
they're very dangerous. They're very dangerous. Yes, you're absolutely right.
That bridge just looks dangerous. The one with nobody else.
Yeah, it does. Yeah.
That one looks like it should not hold a train.
Well, that one.
How long has that been around?
A long time. I actually know a guy who is severely injured crossing that train track without paying. I've known a few people who've been injured in a train versus vehicle accident.
Really?
But yeah, that track has been around. I've lived here since 1989, and it was old at that time. They've rebuilt that approach several times going into Ralston, but it was around. It's been around for a long, long time. The other thing, last closing note, when you're building highways, which are just sort of like the most mega amazing thing in the world, once again, here's Ralston over here, and here's Powell over here, and you come in on the Powell-Cody Highway. When you come into Ralston, I can't remember exactly how that road goes, but there's 3 separate curves before it straightens out. Because when you're coming, and they rebuilt this back in the early aughts, maybe it was about 2000, but the Wyoming Department of Transportation, WYDOT, rebuilt this. But there were some complicating problems, because you need to go from Powell to Cody through Ralston, and you have private ownership issues, and so there is a way that like the highway department can use, there's some laws that would allow them to purchase people's property for reasonable amounts of money, but it's a really bad idea. I mean,
You want to
right, and you will, that's right. So if you can possibly avoid that, you try not to. And at the same time, with this highway, aside from getting from point A to point B without interfering with personal property rights, you also have to make sure that the road is banked and crowned enough that the water will drain properly, because that's another huge problem. And it didn't for a while. They actually had a big drainage problem at one point on this highway. But this actually turns out that it's 3 different parts of 3, they're called Euler spirals, which is a mathematical curve. And so this was kind of an active engineering genius, in my opinion. So there's lots of things like that. But so like if you were designing this highway, and I actually I did talk to some engineers, but I talked to the tech who actually did the staking for this. That was not their first idea. they had other ideas first, but this is the one that worked the best. And I have a feeling they probably used Excel or a design program to help them get to that solution. All right, so that's it for today. I will go ahead and stop recording, but we will see you this afternoon. We will work on the Excel stuff in chapters 1, sections 1 through 111, and maybe some of you will get done today and you won't have to worry about it again. Then we'll go on chapter 2. So we'll see where it is. All right, you guys have a